Hello there, and welcome to Depths of Unknown. Tonight we talk about the unexplained parts of Arctic that scientists can't explain. There are regions of the Arctic that appear on expedition planning maps with cautionary notations that have nothing to do with weather or ice conditions and everything to do with what those regions are currently doing to the atmosphere above them. These are areas where the permafrost, the permanently frozen ground that underlies approximately 15 million square kilometers of the Arctic and subarctic, is thawing, not thawing in the gradual, manageable sense of seasonal surface melting that has always characterized Arctic summers, but thawing at depth, in layers that have been frozen continuously for thousands of years, releasing the organic material trapped within them into conditions that allow microbial decomposition, and producing in the process quantities of methane and carbon dioxide that make the areas directly above active thaw zones genuinely hazardous to work in. The methane concentrations in the air directly above some active permafrost thaw zones in Siberia and northern Canada have been measured at levels sufficient to cause physiological effects in researchers working unprotected, and the unpredictable nature of thermokarst formation. The sudden collapse of ground above thawing permafrost creates physical hazards for field researchers that are difficult to assess in advance and that have caused injuries and equipment losses in multiple recent field seasons. Researchers have arrived at sites that were safely accessible in the previous season to find them transformed, the firm tundra surface replaced by a network of water-filled collapse features, the field camp access routes blocked by new thermokarst lakes, the terrain that had been planned for systematic survey now unsafe for foot travel. The Arctic that scientists are trying to study is in some areas changing faster than the study plans designed to characterize it. But the specific reason that the most serious Arctic scientists describe certain regions with something approaching anxiety is not primarily the physical hazard to individual researchers. It is the data those regions are producing, measurements of methane and carbon dioxide flux that exceed the models scientists have built to predict what should be happening, in some cases by factors large enough to require explanation, in an environment whose behavior has consequences for the entire planetary climate system. The permafrost of the Arctic is not simply frozen ground. It is a geological archive of organic material accumulated over thousands of years in the cold, wet, low-oxygen conditions of the Arctic tundra and boreal forest. Conditions in which organic material does not fully decompose but accumulates, year by year, in the frozen matrix of silt and water and plant remains that makes up the permafrost layer. The organic carbon locked in Arctic permafrost is estimated to represent approximately 1.5 trillion tons, roughly twice the total amount of carbon currently in the atmosphere. This carbon accumulated over the past 12,000 years, since the retreat of the glaciers of the last ice age in the form of dead plant material, animal remains, and microbial biomass that froze before it could be fully decomposed and has remained frozen ever since. To appreciate the scale of this storage, consider that all the carbon released by human industrial activity since the beginning of the Industrial Revolution represents approximately 500 billion tons, a figure that is substantial in its atmospheric consequences. But that is less than half the amount currently locked in Arctic permafrost, waiting for temperatures to rise sufficiently to allow decomposition to begin. The permafrost is, in this sense, a carbon sink of extraordinary scale, a storage reservoir for organic carbon that is maintained solely by the condition of being frozen, and that releases its stored carbon back into the atmosphere as carbon dioxide and methane the moment the temperature rises enough to allow microbial decomposition to proceed. The warming of the Arctic, which is occurring at approximately 3 to 4 times the global average warming rate in what scientists call Arctic amplification, is now thawing permafrost at depths and at rates that were not predicted by the models of even 15 years ago, and the carbon that is being released from this thaw is entering the atmosphere as both carbon dioxide, the product of aerobic decomposition in drier thaw environments, and methane, a greenhouse gas approximately 80 times more potent than carbon dioxide over a 20-year timescale, produced by anaerobic decomposition in the wet, waterlogged thaw environments called thermokarst lakes and wetlands. The thermokarst landscapes that form as permafrost thaws represent some of the most visually dramatic and physically hazardous environments in the Arctic research setting. Thermokarst forms when the ice within permafrost, the ground ice that can constitute 30 to 70% of the volume of some permafrost layers, melts and the ground above subsides, creating irregular depressions, sinkholes, and collapse features that can appear with very little warning and that can be meters deep. In some areas of Siberia, thermokarst sinkholes have opened in the tundra surface overnight, circular depressions tens of meters across that were not present the previous day, driven by the sudden melting of buried ice, wedges whose collapse removes the structural support of the soil above. Researchers working on foot in thermokarst-affected terrain risk breaking through the surface crust into waterlogged ground below, losing equipment to sudden ground subsidence, or being unable to access areas that were safely walkable in previous field seasons. A researcher who steps into an apparently solid tundra surface may break through into a water-filled collapse feature below, a hazard that is entirely invisible from the surface, and that becomes more prevalent each year as the active thaw front deepens. The larger thermokarst features, retrogressive thaw slumps which can be hundreds of meters wide and advance upslope by tens of meters per year, are visually spectacular but physically imposing, with steep headwalls of thawing sediment, unstable slumping surfaces, and active meltwater streams that make them both scientifically important and logistically challenging. The retrogressive thaw slumps of the Canadian Arctic archipelago and the Siberian Arctic have been growing in size and number in recent decades, and the rate of their growth has itself accelerated. Slumps that were mapped as stable features 10 years ago have since expanded to 3 or 4 times their original area, exposing fresh faces of thawing ice-rich permafrost that retreat upslope year by year. Aerial surveys of regions that were stable in satellite imagery from the 1970s show landscapes that have been dramatically altered by permafrost thaw, networks of thermokarst lakes where there was previously continuous tundra, coastlines eroding at meters per year as the permafrost that stabilized them thaws, and river systems transporting massive quantities of dissolved organic carbon to the Arctic Ocean that were not present in the same quantities in historical records. The methane emissions from Arctic permafrost thaw represent the central scientific concern that makes certain Arctic regions particularly urgent for study and simultaneously particularly alarming in their implications. The methane released from decomposing permafrost organic matter enters the atmosphere through 2 pathways that operate on very different timescales and in very different quantities. The first pathway is diffuse emission, the slow seepage of methane through the soil surface from decomposing organic material throughout the permafrost thaw zone, a process that operates continuously over large areas and that contributes a relatively predictable baseline of methane to the atmosphere. The second pathway is the sudden dramatic ebullition, bubbling of methane from thermokarst lakes, where the decomposition of organic material at the lakebed produces methane that is trapped in the sediment and then released episodically in bursts that can be measured by researchers placing collection chambers on the lake surface. Researchers studying Siberian thermokarst lakes have filmed the surface during these ebullition events, the lake appearing to boil as methane bursts through the water in concentrated streams of foamibus, bubbles from specific hotspot locations on the lakebed, locations that produce consistently higher emissions than the surrounding sediment and that represent the sites of most active ancient carbon decomposition. In the Siberian winter, the methane seeping from thermokarst lakebeds prevents the ice above from freezing completely, and the circular patches of open water in the middle of frozen lakes, maintained by the upwelling methane below, are known to local indigenous communities as having always been there as features of the winter landscape that were present before the current warming accelerated their activity. The methane flux measurements from the most active thermokarst lake systems in Siberia and Alaska have in some cases produced results that exceeded the predictions of permafrost carbon models by factors of 2 to 5, measurements that, when first reported, were treated as measurement errors or local anomalies before the consistency of the anomalous readings across multiple independent measurement campaigns established them as genuine signals requiring model revision. The implications of methane emissions at the high end of the current observational range are significant for global climate projections. The permafrost carbon feedback, in which warming releases permafrost carbon that causes further warming that releases more permafrost carbon, is one of the most important potential positive feedbacks in the climate system, and its magnitude determines in part how much warming the Earth will experience over the coming century. One of the most extraordinary and scientifically significant features of the Siberian Arctic permafrost landscape is a geological formation called the Gema, a deposit of extremely organic-rich, ice-saturated permafrost that was formed during the last glacial period, and that covers significant areas of northeastern Siberia, Alaska, and the Yukon. Gema contains extraordinarily high concentrations of organic carbon, up to 5% organic carbon by weight, compared to typical permafrost values of 1 to 2%, and it is also extraordinarily old, with some deposits dating to 50,000 years before the present. The age of Gema organic carbon is scientifically significant because it represents material that has been frozen since the Pleistocene, that has never been exposed to modern decomposition, and whose release to the atmosphere would represent not the recycling of recently photosynthesized carbon, but the net addition of ancient carbon that has been out of the active carbon cycle for tens of thousands of years. The mammoth remains found in Gema deposits across Siberia, the well-preserved specimens whose frozen flesh has been consumed by local dogs and whose hair and skin and organs retain their pre-extinction character after 30 to 40,000 years of preservation, are the most publicly known product of Gema's extraordinary preservation capacity. The same conditions that preserve the mammoths preserve the microbes that lived alongside them. Scientists who have recovered microbial communities from Gema permafrost and thawed them in laboratory conditions have documented metabolic activity resuming in organisms that had been frozen for 30 to 40,000 years. Microorganisms that wake from their Pleistocene dormancy and immediately begin consuming the ancient organic material around them. When these microorganisms activate in the thawing Gema of northeastern Siberia, they are processing carbon that entered the frozen archive when mammoths still walked the tundra above it, and releasing that carbon into an atmosphere that has never previously received it. The scientific instrumentation deployed in the active permafrost thaw zones of the Arctic to measure the carbon flux from these environments represents some of the most challenging field science anywhere on Earth. Eddy covariance towers, instruments that measure the continuous flux of carbon dioxide and methane between the surface and the atmosphere by tracking turbulent air movements, are deployed across the Arctic tundra in networks whose coverage is still insufficient to fully characterize the spatial variability of permafrost carbon emissions. Each tower must be placed on a foundation that does not itself thaw as the permafrost changes, a requirement that has become increasingly difficult to meet as the permafrost below the towers themselves changes, with some towers that were installed on solid frozen ground now sitting on unstable thawing sediment that requires costly reinforcement or relocation. The logistics of reaching and maintaining remote Arctic measurement sites involve helicopter access over terrain that is impassable on foot and that changes between seasons, sometimes rendering planned access routes impossible. Instrument packages must survive temperatures of -50 degrees Celsius, must function through months of polar darkness during which no solar power is available, and must store and transmit data in conditions that destroy electronics designed for temperate environments. The researchers who work in these conditions describe the experience in terms that simultaneously communicate genuine physical hardship and genuine scientific urgency. The knowledge that every data point collected in the thawing permafrost zone is a data point that the global climate models need, that the measurements they are making in these difficult conditions are among the most consequential measurements in Earth science, and that the environment they are measuring is changing around them while they measure it. Helicopter access to remote measurement sites is essential in many areas because the terrain is impassable by other means and because the thermokarst hazards make foot travel unsafe. The researchers who maintain and operate these instrument networks describe their field seasons in terms that combine the vocabulary of extreme physical endurance with the vocabulary of scientific urgency. the awareness that the measurements they are making are documenting a change in progress, whose rate and ultimate magnitude are not yet fully understood. The broader scientific anxiety about the Arctic is not simply about the immediate physical hazards to field researchers or about the technical challenges of making measurements in extreme conditions. It is about what the data are showing and what the data may be underestimating. The atmospheric methane concentration has been rising at an accelerating rate since approximately 2007, after a period of relative stability, and the contribution of Arctic permafrost thaw to this acceleration is being actively debated in the scientific literature. Some researchers argue that the permafrost signal is already detectable in the global methane trend and is growing. Others argue that the primary driver of the current acceleration is different sources, and that the permafrost contribution, while real, is not yet the dominant factor. The uncertainty itself is significant. The difference between permafrost carbon emissions at the low end and the high end of the current observational and modeling range is large enough to make a material difference to global temperature projections this century. There is also a temporal dimension to the scientific concern that goes beyond the current rate of emissions. The permafrost carbon that is being released now represents primarily the surface layers, the shallow permafrost that warms first as air temperatures rise. The deeper permafrost, and particularly the ancient Yama deposits of northeastern Siberia, has not yet been substantially mobilized by the warming that has occurred so far. As warming continues and the active thaw layer deepens, it will eventually reach these deeper, older, more carbon-rich deposits, and the rate of carbon release will depend on how quickly the thaw front descends, a question whose answer depends on the rate of warming, the thermal properties of the overlying material, and the complex dynamics of heat transfer through wet and changing sediment. The scientists working in the thawing permafrost zones of the Arctic are in this sense not studying a problem that is already fully unfolding. They are studying the early stages of a process whose full development extends decades and centuries into the future, and whose ultimate magnitude is one of the most important unknowns in the climate system. The Arctic is sending a signal, and the scientists working in the thawing permafrost zones are trying to understand how loud that signal is and how much louder it will become, knowing that the answer matters to every human being on the surface of the planet, and that the measurement campaign is racing against the very change it is trying to characterize in a landscape that is becoming less safe, less accessible, and more urgent with each passing season, and in which the question of what the Arctic will do next is one that the instruments in the thawing ground are answering one data point at a time, in a language of carbon and methane and heat that the rest of the planet is only beginning to learn to read.